Okay, unfortunately, the microphone didn't work during 2 hours of recording. I'm gonna have to re-record, but of course I got the blackboard, so I'm gonna discuss these things by pointing. Unfortunately, I think it works better for most people if they actually see the things developed in real time, but we're gonna have to go this way. Okay. This one isn't gonna work if I just point at it, because you already see what the solution is. We build this one more step by step. So we have a problem. We have radioactive decay, 60 decays per second, down to 24 decays per second in 4 minutes. So the radioactivity is decreasing. We sketch a graph. And sketching the graph, we just put our 4 minutes here. We put our y equals 60 here, y being the number of decays per minute. And so we have this line and the line for y equals 24. We note that 24 is 40% of 60. So in 4 minutes, we go down to 40% of what we have. And we can compare that with the half-life. The half-life, well, we're going to get down to half a little quicker than we're going to get down to 40%. So we could also talk about a half-life where y equals 30. In other words, if we start at 60 decays per second and go down to 30, that's a half-life. To see the shape of the graph, of course, you already see a shape, but how did I get that shape? Also figured out that in the next 4 minutes, in the first 4 minutes, we go down from 60 to 24. In the next 4 minutes, we go down to 40% of 24 because we always end up on any given time interval, we end up with the same percent of what we started with. So if we have a 6-minute time interval at the beginning, 6-minute time interval sometime later on, we're going to lose the same percent in that 6 minutes. Okay, well, down to 40% of 24 puts us at 9.6. So we write a line for y equals 9.6. I don't think it's particularly accurately done, but let's say there it is. At 8 minutes, we'll be down to 9.6. We start at 60 with t equals 0. We sketch a curve and looks like reasonably like an exponential curve. We also then estimate what the half-life is. We estimate it's about 3 minutes, meaning that we hit from 60, from y equals 60 at this time, we go down to y equals 30, and we have this point on the graph. So this is how long it took. Looks like about 3 minutes, about 3 on a scale of 4, maybe even a little more, probably not much. Okay, now we want to find a formula for this function because problem asks to, I forget exactly what the problem asks right now. It's on your sheet. Okay, so in order to find the formula, we got to decide what form of an exponential function we want to use. Well, y equals ab to the t is probably the simplest model. We could have also used y equals ae to the kt, but we didn't. So I'll just kind of say, oh, we didn't use that one. It's not a bad model. It's a very good model, as a matter of fact, and much more amenable to the use in calculus. But right now, we'll just stick with y equals ab to the t. Our point 0, 60 tells us that y is 60 when t is 0. So we get 60 equals ab to the 0. Y equals 24 occurs when t equals 4. So we get 24 equals ab to the 4th, and we easily solve this system of equations. We can't solve it using elimination, which is something we've been stressing even more recently. But we can use substitution. For example, let's solve first equation for A. Okay. Well, the first equation is 60 equals AB to the 0. B to the 0 is 1, so we just get A equals 60. Well, we're done there. Okay. Now, if we don't have the t equals 0, there's something else we have to do, so make sure you review that. Okay. Then that gives us equation one. Equation two then gives us, now I was handling the board, so I kind of messed it up, so I get to write this. 22 equals 60 b to the fourth. Because of course, we put 60 in for A here. We get 24 equals 60 b to the fourth. And we take that over here, and we can write then b to the fourth is 24 over 60, just dividing both sides by 60. And that's 0.4. Okay, then we take the 1/4 power of b to the fourth. Power of a power, we multiply the powers. 4 times 1/4 is 1. So this gives us b to the 1 on this side. On this side, 0.4 to the 1/4 is around 0.8. If you square 0.8, you get 0.64. If you square 0.64, you get something just a little over 0.4. So closer to 0.8 than 0.7, probably 0.7879 would do it. This gives us a model then. Y is approximately equal to 60 times 0.8 to the t. Approximately, because this value b is only approximate. The half-life, t half, well, there are many ways to get it, and I've showed other ways. But the easiest way, if we know what the amount is at t equals 0, that would be y of 0. This is function notation, not y times 0. Y evaluated at t equals 0. Then y at the half-life will be 1/2 of y at t equals 0. T equals 0, y is 60. At t equals 1/2, y looks to what y is going to be 30, whatever the half-life is. Okay, so we solve this. Y of 0 is just plug in 0 to our function, 60 times 0.8 to the 0. That's going to equal 60 times half that is going to be 60 times 0.8 to the t half. We're just saying that at the half-life, it's going to be half as much as it was at t equals 0. We do the numbers, and we quickly get to 0.8 to the t half equals 60 over 30, which is 1/2. So that t half is log 0.8 of 1/2. Just write out the equation. 0.8 to the t 1/2 equals 1/2. Convert it to logarithmic notation. You have this. And the log 0.8 of 1.2 is a log of 1/2 of the log of 0.8. And that comes out, I think, pretty close to 3. All right. So that's one thing we can do in a typical radioactive decay problem. Anytime you have 2 points on an exponential function being one that has a constant half-life, it's of the form a b to the t. We can get 2 equations from 2 points, and we can solve those 2 equations. Okay, so now here's a problem that we will look at, but want to keep things more or less in order. So we move to problem number 6 on the sheet. And let's move this over so we can see it all. Okay. So we have a problem, number 6. You can read the problem. It tells you that a profit on May 1st is some number. Now the number was 2850 or something like that. I rounded to 300, and then I started using, or 3,000. Then I started using 6,000 because I've got a 6 here. I just kind of confused the numbers. It doesn't matter. Whatever the numbers are, here's how you set it up. Okay, so profit on May 1st is $6,000. It increases by $6 per day during the month of May. So what's the profit on day N? Well, if your profit on day 1 is 6,000, you can put this on a graph. You can put t equal 1 here. That stands for day 1. And you put the profit up here at 6,000, profit in dollars. And I should have written dollars here, but trying to get a lot done in a short time. Okay. So you have a graph that kind of looks like this. Between t equals 1 and t equals n, well, your change in time would be n minus 1. So maybe that's an n minus 1 day time interval. Okay, and you want to figure out what the change in p is. We don't have enough information to do that on the graph unless we know what the function is. Now, this line represents a linear increase in the profit. It changes by the same amount every day. At least we're assuming that. That's probably not a realistic assumption. But on the average, that might be the case. Okay, so we have this linear increase, and here's this function, and it has a formula that let's figure out what the formula is. Okay, in n minus 1 days at $6 per day, how much is the profit going to increase? Going to increase by 6 times n minus 1, whatever n happens to be. So the profit will be $6 times n minus 1. That's going to give you a profit of $6 times n minus 1. That's going to be the change in the profit. Now, the original profit was 6,000, and we're adding this daily profit. So there we have a model for how much profit. We have the $6,000 profit that we started with. We're adding $6 a day for n minus 1 days. So we can say our profit function is 6,000 plus 6 times quantity t minus 1. Now, what do I use t instead of n? Well, t is our independent variable here. And we started with the assumption that t was equal to n. We figured out what this was, but we might as well just call it t instead of n, so there it is. Okay, so now our profit function is 6,000 plus 6 times t minus 1. Notice I left the dollar sign off here, don't want to confuse the issue, but we understand that p is in dollars. So maybe we put a dollar sign here. Then this line represents our profit as a function of time. Now we can simplify this expression using distributive law. We get our 6t minus 6, and then subtract the 6 from 6,000. Profit is 59.94 plus 6t. There's a little weird about what I did here. I didn't say when on May 1st the profit was $6,000. So I just said, well, that's what we're going to associate with day one. We might say the profit was 0 at this point and get a slightly different profit function, but either way, it's going to be okay. All right. Now, there's another problem that I didn't number, and I'm not going to go back and find the number. Because this doesn't exactly correspond to any problem. There are a couple of problems that involve finding the two functions you need to make a given composite. So we want to find f and g such that, well, we try to break this 2 times quantity x plus 5 squared into a composite of two functions. That means we're trying to find f and g so that f of g of x equals 2 times the quantity x plus 5 squared. And that function we're going to call h of x. Okay, well, to do this, one way to find the g of x function is ask yourself, well, what's the first thing that happens to x? Well, the first thing that happens to x is you're adding 5. So we could start with g of x equals x plus 5. First calculation on x is g of x equals x plus 5. Now, what would you plug that into to get 2 times the quantity x plus 5 squared? Well, if you plug x plus 5 into f of x equals 2x squared, what do you get? Well, if you plug g of x into f of x equals 2x squared, x gets replaced by g of x here as well as here. You get 2 g of x squared, and if g of x is x plus 5, then you get 2 times the quantity x plus 5 squared. So again, what's happening is, first thing that happens to x is you add 5 to it. Then once you got that x plus 5, you plug it into 2x squared, replacing x by x plus 5, and you get this. Or what happens after you get the x plus 5, you double it and square it. What function doubles and squares? 2x squared function. Okay, so that f of g of x, if f of x is 2x squared, g of x is x plus 5, gives you this. Now we talk a little bit about what happens if you have a system of linear equations. Okay, well, here's a system, 2x plus 6y equals 24, 5x minus 3y equals 12. We're not actually going to solve this system because we've been doing this recently. You've seen plenty of examples of it, and you can find as many as you like on the internet. Okay, but there's plenty. You know, you've used the open math. There are videos there. You've got my videos. Find the video you like best, or find the explanation you like best, and make sure you can do everything I'm going to talk about here. So, what are your solution methods? You got 4 different possible solution methods, only 3 of which you know how to execute. Solution method substitution, where you, let's, for example, solve equation 1 for y and plug that in to equation 2. So you've solved this equation for y, and whatever you get is going to have just an x in it. So it's going to be a function of x. So you plug it in here, and now this equation will be expressed only in terms of x. And it's going to be a simple linear equation that you can solve for x. After you solve this equation for x, you take that x back up here, plug the number in, and now you have something you can solve for y. That should be familiar. Now, in the class, we've emphasized more elimination and use of augmented matrices, and also being able to write this as a matrix equation, even though we didn't take this to a solution. See what I mean? In elimination, well, I'm not writing it out, but if you multiply the second equation by 2, you're going to get a negative 6y to match the 6y you've got here. So that when you add the equations, meaning add the left sides and add the right sides, y is going to disappear, and you're just going to have an equation in x. Similar to what you do if you solve the first equation by substitution, plug in, you get an equation for x, and you solve that equation and plug that x back in to either of the equations in this case, and you're going to be able to solve for y. Then, of course, you want to check. And we haven't done the detailed solution here, so we're not going to actually do the check, but you always want to check to make sure you're right. Augmented matrix, well, we can write this as an augmented matrix, and this should be familiar. First equation, we just eliminate all the plus signs and equal signs and write the coefficients. You know, we understand that the first column is the multiple of x. Second column gives you the coefficients of y. And the third column gives you what's on the other side of the equal sign. So we're representing these 2 equations with this augmented matrix, and now we want to reduce it. Easy enough. Let's divide the first equation by 2. It's going to give us a 1 here. And that's going to give us a couple of other numbers. Yeah, they would be 3 and 12, but we're not going to write those out. Okay. So we put the matrix into this form. For now, these numbers are just whatever follows when we do the row operation. Okay. Which is simply dividing first row by 2. Having done that, we can multiply this first row by negative 5 and add it to the second row, which is going to give us a 0 here. And that's our goal. Get a 1 here and a 0 here. It's the first goal. Having done that, we can divide this number, or we can divide the second row by whatever number comes out here. And we're going to get a 1 in this position. So now we have a 1, a 0, and a 1. And then I think I need to move the board over a little bit. Then we multiply this row by whatever this number is, or the negative of whatever this number is, and add it, and that's going to give us a 0 here. And now we have a 1, 0, 0, 1, what we call the identity matrix. And the first row tells us that x equals whatever this asterisk is. Okay. The second row tells us that y equals whatever this double asterisk is. Now I used asterisks throughout until I got down to here. I put a double asterisk here so we can tell x from y. We don't know what the numbers are going to be, but if we do the operations that I said, we're going to find out. Okay, then this is the beginning of a solution method. You have a matrix equation. This matrix equation gives you this system because when I multiply the row 2, 6 by xy, well, I get 2 times x and 6 times y. 2 times x, 6 times y. And that equals whatever's in the first row over here. Since I used the first row, it's got to equal what's in the first row, which is 24. So there's our first equation. Our second equation, we multiply the 5 by the x, the negative 3 by y. We get 5x minus 3y, and that's equal to the number in the second row, which is 12, and there's our system. So we can translate the system to a matrix equation. This is a very efficient way to solve things, actually, because then you can do what's called the inverse of this matrix, multiply both sides of the equation by the inverse matrix, and you get xy equals the inverse matrix times 24, 12. Very simple matrix multiplication, and you have your solution. To find the inverse matrix, well, I could explain it to you in 15 minutes. I'll just tell you now, just in case you're curious, but you can ignore this. You take 2, 6, 5, negative 3, then you augment this with an identity matrix. And then you do row reduction operations to get the 2, 6, 5, negative 3 down to 1, 0, 0, 1, the same operations that we would have used to reduce this matrix. And this gives you 1, 0, 0, 1, and some numbers over here. And these numbers are your inverse matrix. If you take this matrix then and multiply it by this matrix, you get the identity. And if you multiply it by this matrix, you get your solutions. Okay, you don't need to know that. It's not going to be in the test. You want to show off, go ahead and write that down, explain what I just said, and I'll give you some extra credit. So I'm going to leave it there, but I'm going to kind of say, well, that's just kind of in parentheses. We don't really care about that much. Okay. Now, another problem. You got $9,000 at 3%. I think that is the way the problem is stated. Again, I don't remember what the number of this problem was, but you can easily identify it if you have the document. So you have $9,000 at 3% compounded monthly. What does it mean to compound monthly? It means you get 1/12 of 3% every month. Well, why is that better than just getting 3% at the end of the year? At least by the end of the year, wouldn't you have the same thing? Well, no, you wouldn't, because you apply this half of 3% every month applied to what you had at the beginning of the month. Now, at the beginning of the first month, you've got $9,000, but at the end, you have more than 9,000 because you got 1/12 of 3% of 9,000. Okay. So you got, but close to $20 more. I think you do the arithmetic. So what happens then is every month you get to add 1/12 of 3%, which is 1/12 of 0.03, which is 0.0025 of what you have here. Okay. Adding the 12th of 3% is adding 0.0025 of whatever your principal is. And that's the same as multiplying your principal by 1 plus 0.0025. If you multiply 1 plus 0.0025 by $9,000, you get 1 times $9,000 plus 0.0025 times $9,000, meaning you get your $9,000 plus the interest. Okay. Now, you then take whatever you get from this and multiply by this again. And you get the amount at the end of the second month, which is, you're going to have a little bigger increase than you did in the first month, because at the beginning of the second month, you have more money than you did at the beginning of the first month. I want to try to understand that. That's the principle of compound interest. Okay. Now, after n months, you will have multiplied by that 1 plus 0.0025 n times. And you have $9,000 times 1 plus 0.0025 raised to the nth power. We did this in detail in class. You might want to review it. Now, I use the 1 plus r over 12 here, because that's in a formula your book gives you instead of explaining what's going on. It's 1 plus r over 12. That's your 1 plus 0.0025, because what's r? R is your 3%, and 12 is the number of times you're compounding. And I'm confusing the value of n. I just realized that you're probably using n for the number of compoundings, but just take this for what it's worth. Okay. Don't want to confuse the issue further by explaining how I confused the issue. In T years, there are 12 T months. So if n is the number of months, you've got 12 T months, you're going to replace n by 12 T. Now you got 9,000 times 1 plus 0.0025 to the 12 T. And of course, 1 plus 0.0025 is 1.0025. So you're going to be raising 1.0025 to the 12 T multiplied by 9,000. Now that's very much what the formula given in your book tells you. I recommend that you understand what's going on here rather than try to memorize that formula, because I'm not going to give you the formula on the final. But if you want to memorize a formula and apply it, it's okay. If you understand it, you probably don't really need to memorize it. But if you understand it, you probably have it pretty well at your fingertips. Anyhow, you got 9,000 times 1.025 to the 12, to the 12T. But that's the same, 1.0025 to the 12T is the same as 1.025 to the 12th raised to the T power. Because, of course, a power of a power, you multiply the two powers. T times 12 is the same as 12T. And this, you see, is the form A, B to the T, where B is your 1.0025 to the 12th. So this is a simple exponential function. Okay, so try to understand that. It's fairly fundamental. I've got a clean stretch of board here so I can talk about the first problem, which I marked. The first problem was actually, we didn't have the first problem here. Where in the world is it? Oh, now I'm all confused. What's going on? We have that. Okay, it's here somewhere. At least it should be. I'm going to pause the video while I find the problem, because we just had it up there. Okay, the first problem actually that we did that I didn't want to do because the whole answer is on the board and this really needs to be constructed. We have a polynomial, and you can read this problem. It has three zeros, okay? So you know what you do with zeros. You have a zero at x equals -3, and it's of degree 2. So we're going to do a line here for x equals -3. And we're going to note that the degree is 2. We have a 0 here. We have a 0 at x equals 1. And a 0 at x equals 6. My scale's a little off, but that's okay. These are both of degree 1. The y-axis is going to be about here. That's x equals 0. And the y-intercept is said to be at 14. So we draw a line for y equals 14. Now, these numbers don't match the numbers on the problem that you have on the sheet. You reason it out for the numbers on the sheet. But here's this is what you do. If you're given 3 zeros, that's going to be 3 points on the x-axis, 3 x coordinates, of which y is 0. In other words, 3 points on the x-axis. You're given the y-intercept, and you're given the degrees of the zeros. Now you're asked to figure out what the graph is going to look like. Okay. Yeah, I did it right. Okay. Either the graph, well, okay, start here. These 2 points are zeros of degree 1, meaning either you're going to go through this point this way and this point this way, or vice versa, like so, this way and this way. Since your y-intercept is here, you've got to go down from here to get through this 0. So you're going to have to go down this side and then come back up on this side. Okay, so we know that the graph is going to somehow have to do this. And then it's just going to have to keep climbing. We'll say a little bit more about that in a minute. Now, you've got a 0 of degree 2. You've got to be above the x-axis when we go through here. So we've got to be above here, and then we've got to come down. And then we're going to go back on up. The graph is going to behave like a transformed squaring function near this point. Okay. It's going to act like a linear function at these points, like a transformed squaring function at these points. We've explained this to some extent. But this is what a degree 2 0 looks like. This is what degree 1 zeros look like. So we get a graph that looks pretty much like this. If you zoom out, the graph is going to look like this with a couple of wiggles close to the y-axis. Okay, got that little blue blur indicates these wiggles. Let's get the formula or a formula for this function. Well, we know that y is going to equal, well, to get a 0 at x equals -3, we've got to have x minus -3 or x plus 3. And that 0 is going to be of degree 2, only if this is squared. And then we're going to have a 0 at 1. Well, that comes from a factor x minus 1 and a 0 at 6. So we're going to have a factor x minus 6. Now, there might be other factors, but we have at least this, and this. We also have a number out in front that I'll call A that we're going to regard as unknown. Reason we have to have an A out in front is because we just had this without a number in front. Then when x equals 0, we'd have 3 times -1 times -6, which is -18. That was positive 18. We wouldn't have 14. In other words, the y-intercept here, if we don't have some number in front, is going to be 18. To get the y-intercept that we've stated here, we've got to have that number in front. Find A. Y-intercept is at 0, 14. So y equals A times x plus 3 times x minus 1 times x minus 6 is 0. Sorry, y is 14. Equals A times 0 plus 3 times 0 minus 1 times 0 minus 6. So 14 equals 18A. So A equals 14 over 18, which equals 7 over 9. So that our function now, well, we figured out what the function is, or at least the function of least degree. Now that matches what we got here. Right out we locate our zeros, note the degrees, 2 here, 1 here, and 1 here. Note the y-intercept, which I didn't really mark. There it is. And here's how we develop our equation. So pretty much identical to what you just saw me do. All right. Let me keep things in order. Okay, I think that much we did in the support course. Then we started here. And I'm going to just do one video for the support course and pre-calculus course. Okay. Now I gave everybody, because we had a lot of problems getting the document. The printer wasn't accepting document. So I had to step out for about 5 minutes and go get a document that I had to ask somebody else to print. Got a function g of x equals a f of x minus h plus k. And the thing I asked people to do while I was gone, which wasn't exactly what's on the document that we're working from, was let f of x be one of the toolkit functions. Pick one, any one. Okay. Then I said, well, let h equal 7, let k equal -5. And see what function you get, and then evaluate g of 2, g of 4, g of 6 over g of 2, etc. So I kind of recommend that as an exercise using different toolkit functions. For this particular function, I said you could use this if needed. That doesn't correspond to this h, this k, and this value of a. But if you're doing what I asked, let f of x be toolkit squaring function, toolkit reciprocal function, toolkit exponential, reciprocal square, cubing, whatever function you want, you can do this exercise, okay? And use it, you can maybe pick your own values of h and k. All right. So what I proceeded to do, since different people chose different functions, okay, I forgot about this one. And I said, okay, we're going to just suppose f of x is the toolkit squaring function. Then if a is 3, h is 7, k is 5, g of x would be -3 times quantity x minus 7 squared minus 5. This g of x, this f of x. And that's a function that we went ahead and work with. Okay, so what's g of 2? Well, g of 2 means you're going to replace x by 2 here, because there's a 2 where there was an x. So this x had better be 2. So you're going to get -3 times x, which is now 2, then -7 quantity squared minus 5. And you can evaluate that. You're going to get what, negative 15 minus 5, negative 20, I think. Then g of 4 minus g of -2. What's g of 4 minus g of -2? Well, you have to calculate g of 4. If you put 4 in for x, you're going to have 4 minus 7, which is -3. Square that, you're going to get 9. -3 times 9 is 27 minus 5 gives you -32. Figure that out yourself. Okay. And I think if you plug in -2, well, you're going to be squaring then -9. -2 minus 7 is -9. You square that, you get 81. Multiply it by 3, you get 343, but it's -343. Uh-oh. Negative 243, I'm sorry. Negative 243, and minus 5 gives you -248. Okay. Yeah, 343 is what you get when you cube 7. So it just kind of popped into my head, but I had it right the first time. Okay. G of 6 over G of 2. Well, it's getting a little monotonous here. You just plug in 6 for x, and you get this. And then you plug in 2 for x, and you get this. And I think if you work out the numbers, you get -8 over -80, which reduces to 1/10. Now we get into somewhat more interesting expressions. What's g of x plus delta x? Well, you see, g of x is this. Compare g of x with g of x plus delta x means x has been replaced with x plus delta x. So we've got to write an x plus delta x wherever we got an x, and that's what we get there, here. Okay, so if we replace x by x plus delta x, this expression becomes this expression. We don't write out this expression and then a plus delta x on the end. It's not replacing x by x plus delta x. Okay, we got to replace x by x plus delta x. Now, this can get a little complicated, and it's complicated enough that I didn't want to take time to actually expand the x plus delta x minus 7. It would be a good exercise, good practice for you to do that. Okay, you take, but anyhow, you expand this square, use a distributive law, x plus delta x minus 7 times x plus delta x minus 7. Multiply that by -3, subtract 5, you get g of x plus delta x. Okay, Now we did g of x plus delta x minus g of x. There's method to my madness. I'll explain that in a minute. G of x plus delta x, well, we just write down this expression again. And g of x, we just write down this expression, and this is what you get. This minus this. Now you put all this in parentheses because you're subtracting the whole expression. Then you can simplify that. It'd be a good exercise, especially if you're going to have calculus in your future at any time. And then that equal them. Okay, and we're done with that. Then we got g of x plus delta x minus g of x, which is just this expression, divided by delta x. Well, here's your g of x plus delta x. Yeah, okay. Here and here. So this is here and minus g of x, which is here. If you do the algebra and if you know the distributive law and can write things out coherently, and you should certainly be able to do that by this point, you can simplify this numerator. Turns out when you do a lot of stuff, just kind of cancels out, okay? Like you got a -5 here, and you got a -5 here, the 5 is going to go away, okay? And other stuff is going to go away. And what you're left with is going to be really an important quantity, okay? Just to demonstrate, got any old function g of x. Now it's not this function because this function would be a parabola opening upward, opening downward. I'm sorry, it's got a negative here. So your function is not going to look anything like this thing that I sketched here. But if this is x and this is x plus delta x, then this point is got to be in the line where y equals g of x. And this point is on the line where y equals g of x plus delta x. Then you can do a fundamental triangle here. I'm just starting and I'm not writing the whole thing. You got a delta x here. And you got here, if you can read it, well, you're going to take this and subtract it from this. And that's how far you go here. You're going from here to here, so you subtract g of x from g of x plus delta x. Okay, so this distance here, this arrow here represents g of x plus delta x minus g of x. So that the slope of this line is g of x plus delta x minus g of x over delta x. This is an important quantity. And what you do within calculus is just ask yourself, okay, let's simplify it all. And now let's pretend x is so tiny, or delta x is so tiny, meaning these points are so close together that they might as well be almost the same. Not a great sentence, but we're going to get a quantity that's the actual slope of this graph at this point. Okay, so we do what we say the limit as delta x approaches 0. Now you've done limits as x goes to infinity and negative infinity to get long run behavior and so forth. So that terminology might be familiar. Now you're not going to need to know this, about the graph and everything for the exam. You might have to simplify something like this, but I'd probably give you something simpler than this function. Okay. Okay, we've done that and we've done that. And let's keep it in order. So Class selected certain problems that they thought were ones they weren't completely sure of, things they wanted to see me solve or at least talk about. So one of them was find the domain and range of this function. Now, domain is pretty easy, okay? In this course, at least. For the functions that we're dealing with in this course, your domain is pretty much just restricted by the fact that you can't have a square root of a negative and you can't have a zero in the denominator. Now, there are other restrictions like the square root of x. Well, x has to be greater than zero. Log of x has to be greater than zero. Just think of the graph of log of x. And you should be able to construct that as the inverse of an exponential graph. It's going to look like this. Okay, kind of. It's going to be asymptotic to the y-axis, just as the exponential function is asymptotic to the x-axis. You should understand that. Okay, so no square root of a negative. Yeah, we're doing a pretty abbreviated explanation here. What you're taking the square root of is negative 3x plus 4 quantity minus 4. And that has to be greater than or equal to 0 because there's no number that you can square, no real number at least, that you can square to get a negative. So we solve this inequality, which is very straightforward until you get down to this step when you've got to remember that dividing by negative 3 reverses the inequality. And you find that x has to be less or equal to negative 8/3, which is negative 2 2/3. Okay. So we have this restriction on the domain. You can't talk about x's that are greater than negative 2 2/3. If you do, you're going to get a negative under the square root. Okay. Then the denominator can't be 0. Well, that's really easy in this case. The only way denominator is going to be 0 is if x plus 4 is 0, in which case x will be negative 4, or x plus 3 is 0. So x plus 3 has to be not equal to 0. X can't be equal to negative 3. I'm big on putting my logical connectives in here. So I'm going to write or. In any case, that means your domain goes up to negative 2 2/3, but it can't include negative 4 or negative 3. And negative 4 and negative 3 are both less than negative 2 2/3. So we got to take them into consideration. Okay, so there are two ways I can explain this. I'm debating. Your domain is interrupted at negative 4. Any number less than negative 4 will be less than negative 8/3, which is your negative 2 2/3. So we got 8/3 here, we got negative 4 here, and we got negative 3 here. Okay. As far as the numerator is concerned, any number less than negative 8/3 is fine. However, as far as the denominator is concerned, you can't have x equals negative 4. So at x equals negative 4, we indicate that it can't be x equals negative 4 by an open circle. But also, there's no other restriction as we move to the left. Okay, x can be any number less than negative 4, and it's still less than at negative 8/3. Okay. Now, x can't be negative 4 and it can't be negative 3, but it can be any number between negative 4 and negative 3 because all these numbers are less than negative 8/3. Or it can be between negative 3 and 8/3, but it can't be more than 8/3. So we have an open circle at negative 3, and we have a closed circle on negative 8/3 because negative 8/3 would certainly be in the domain since x can equal negative 8/3. Now it'd give you numerator of 0, so the whole fraction would be 0, but that's perfectly legitimate. But if you go beyond here, you start getting imaginary, non-real square roots. So one way of indicating the domain is just do the whole arrow from -3 on, then put a open circle at x equals 4 and an open circle at x equals 3. And of course, you can express that domain in interval notation. Everything from -infinity to -4 is good. Everything from -4 to -3 is good, except for -4 and -3, right? And everything from -3 up to -8/3, the small interval there, is good. So there's your domain. Now, to get the range, you kind of have to graph the function. And it turns out the graph looks something like this. At x equals -4, you have a 0 of the denominator, and it has multiplicity 2. This means, okay, the graph of the reciprocal square function looks like this. So the graph is going to approach this x equals -4 as a vertical asymptote the way the reciprocal square function approaches the y-axis. Except, of course, it could be upside down, okay? And that's the case. When if x is close to -4, x plus 3 is negative, because -4 plus 3 is -1. Anything close to -4 will give you something close to -1 here. This is negative, this is positive, this is positive. So the function is negative when x is close to -4. So you take this reciprocal square graph, you multiply it by a negative number, and you get something that looks like this. Okay, and you have these asymptotes then. The x equals -4 line. What do you do with that? Well, the only place f of x is equal to 0, I didn't do that graph quite right, did I? The f of x can be 0 when x equals 2 2/3. Okay, so when x equals -2 2/3, you actually have 0 here. And everything is positive. So it turns out the graph is going to go through 0, like here at x equals -8/3. Going to come down here, then it has to come back up and approach the x-axis. Okay, and I'm pretty sure that's right. And this is now. You have to come up from the x equals -4 line as an asymptote, and also from the x equals -3 line. That asymptote will be just an upside down, right side up, inverse square type thing. So it's going to be like asymptotic down here and asymptotic up here. I don't want to go into too much detail about that. The point is, if you graph this function, you can see pretty well that any y value is going to be possible. The y values along this curve go off to infinity. The y values here go to -infinity. You've got a point where the function is 0. And you got points here that go all the way up to 0, and points here that also do that, so that the range appears to be -infinity to infinity. For any point on the y-axis, wherever the y-axis is from here, any point on the y-axis, you're going to be able to hit a point on the graph, including for y equals 0. Okay. It's more detailed than you want. The other way to determine the range is to switch x and y and then solve the equation you get for y, and that would be a royal pain. So we're not going to ask you to do that for this type of function. For simpler functions, yeah, might have to do that sort of thing. Okay. That was number 21. number 22 on your list is the graph this. Okay, so it should be y equals, that's number 22. Fairly straightforward to graph this. It's just simple rational function. Your numerator can be 0 if negative 3x plus 8 equals 0, or x minus 9 equals 0. That gives you x equals 8/3 or x equals 9. So at x equals 8/3, you have a 0. At x equals 9, you have a 0. You have a y-intercept. You let x equals 0, and you're going to just get 8 times negative 9, which is negative 72, over 6, which is 12. Negative 12, sorry. Okay. So y equals negative 12. There's your y-intercept. You have to go through these 3 points, and you have to have a vertical asymptote at x equals negative 6, because that's where the denominator is 0. The denominator is 0 when x equals negative 6. It's just x plus 6 in the denominator, just x plus 6 to the first power. So this acts like, very much like, in the vicinity of x equals 6, very much like the reciprocal function 1 over x shifted 6 units to the left. And that's what it would look like, except it's going to be negative, because near x equals negative 6, this is positive, but this is negative. So that everything except the x plus 6 gives you a negative. So we're taking the reciprocal square shape and we're reflecting it around the x-axis because everything goes negative, and we get something that looks like this, which we see here and here. Then we come up from down here, we go through this point, we go through this point. We go through both of these points along straight lines because both of these factors of the numerator that give us the zeros are linear. So it acts like a straight line in the very near vicinity of this point and in the very near vicinity of this point. Now, away from those points, it curves around, so we get from one point to the next, but there's what it looks like. Now, it doesn't really look like that, because I kind of got a little hump here, because I was trying to fit it to the curve. I think I probably should have come up more like this, and then come around like so. Maybe. I still got a little hump in it. It's something my arms do. Okay. Now there's more to this. The long run behavior of this. Well, if we multiply out, use a distributive law to multiply the two factors of the numerator, we get negative 3x squared plus 45x minus 72. Assume I did it right. Okay. Over the x plus 6. Long run behavior. The degree of the numerator is 2, the degree of the denominator is 1. Matter of fact, the leading coefficient of the numerator is negative 3x squared. Leading coefficient of the denominator is x. If we divide negative 3x squared by x, we get negative 3x. So this thing's going to behave a whole lot like negative 3x when x gets really big. If x is really big, the 45x and the negative 72 don't amount to anything. If x is 1,000,000, then this is pretty close to negative 3 trillion, and this is pretty close to 1,000,000, okay? And the 45x would be close to 45, well, anyhow. These numbers get insignificant when x gets really big, meaning when we zoom out, this is going to look a lot like negative 3x, except near the origin where we have this behavior. All right. The other thing though is that negative 3x is a linear function. If you have a linear function, you get a slant asymptote. So to get the equation of the slant asymptote, we've got to actually divide this into this. So we do a long division. X goes into negative 3x squared, you get us negative 3x. Multiply that by x plus 6, we get negative 3x squared minus 18x. We subtract this from what we have up here, and we use little auxiliary plus signs to remind ourselves that when we subtract these things, we're going to be adding the quantities that we see. We get 53x minus 72 when we subtract. So x goes into 53x 53 times. Multiply 53 by x plus 6, we get 53x plus 168. We're going to subtract those with the little negatives there. And we get a remainder of negative 240, meaning that the quotient is negative 3x plus 53 minus 240 over x plus 6. So this straight line here that this thing is asymptotic to is negative 3x plus 53. So it's going to be 53 units above the x-axis. It's going to be up so high I can't draw it. But it's going to come down like this, and eventually this line is going to become asymptotic to that negative 3x. And this one will actually turn around and become asymptotic to your negative 3x. And actually, well, yeah. So we're not going to try to draw that, but that's how you analyze this. Okay, now I might have covered everything, but let's just make sure. All right, now those are the problems that we had time to do in a little more detail in class. This being the last class, gotta wish you luck on the final. The final exam will be in the testing center by Monday afternoon, needs to be taken by closing on Friday. Now, if Friday happens to get snowed out, I'll probably accept exams on Monday. Testing center will be closing at 5, I believe, on Saturday, and then again on Monday because we'll be in the break. Or we'll be outside the exam schedule. I'll email the details, but it's going to be very similar to the midterm in the way it's administered. You can expect to see a lot of problems of the nature that are on the sheet. You can expect to see some other problems that I've worked, problems of type I've worked in the last week or two. Trying to think if there's anything else. It's late in the afternoon. I'm sorry, I'm a little fuzzy because I had to redo this whole video. So I don't think there's anything else except good luck and have a great Christmas, great break, and hope everything goes well for you in the spring. Okay. Enjoyed teaching class, enjoyed working with those of you who are still working, and even with those who are no longer still working. So best wishes, and let me know if you have questions. I do have office hours that will be posted for next week. And I don't think I'll have any more this week. Any other questions, please just get them to me, and I'll do my best to give you a good answer as quickly as possible.